Hi, in this video we are going to discuss the two-ray model. So why this is called as a two-ray model? Because here we consider two different rays. One is the line of sight wave and another one is a ground reflected wave. So we consider the effect of both of these waves at the receiver side and calculate the path loss and a gain. That's why this model is called as a two-ray model. Another name of this model is the ground reflection model. Okay, so we will discuss how it works. So normally in case of a free space propagation model is provide accurate results in many cases when it is used alone. That means only when a line of sight path is exist, your free space propagation model will give the good results. But this new model called as a ground reflection model or a two-ray model is designed for working with both line of sight and reflected rays. So this model is accurate for predicting the large scale signal strength over a large distance. That means for a distance of several kilometers we can use this model to predict the power. But the assumption made here is that the earth is assumed to be the flat surface. So with that assumptions we are going to derive the power signal strength. So this is the diagram which we used to calculate the received power calculation. So consider this is the ground and it is considered to be a flat. Since it is a reflecting surface, we are marked with this slashed line. So it indicates it's a reflecting surface. So at this point, we are placing our transmitter at the height of HT from the ground plane. Okay, so here our transmitter is positioned from the height of HT from the ground plane, whereas our receiver is at a distance of small d from the transmitter and which is at the height of HR from your ground plane. Okay, as I said, there are two rays. That's why it is called as a two-ray model. The first ray is a line of sight. So the energy along this line of sight path is indicated ELOH. Okay. So which is indicated by this arrow mark from transmitter to the receiver. Where there is another way starts from a transmitter which is not traveled in a straight manner as like LOH, but it is hit on the ground surface and due to the reflection phenomena it get reflected back and finally it reaches the receiver. Okay, so the incident angle is theta I and your reflection angle is theta naught and the total energy at your receiver side is calculated as energy due to the line of sight plus energy due to the ground reflected path. Okay, so this is incident energy, this one is a reflected energy. So this reflected energy is equivalent to the ground reflected energy, EG. And now we are calculating the E field in a free space propagation. So the electric field is calculated at the distance of d for the time small t. So that's why it is indicated as the function of d and t, distance and time. So which is equal to E naught into d naught by d cos 2 pi fc t minus d by c. So in this equation, the E naught is the free space electric field energy, electric field strength, where d is the separation distance between your transmitter and the receiver, whereas d naught is the reference distance that we consider for a calculation. Okay, where this HT and HR are considered for framing this equation for calculating the electric field, where HT is the transmitting antenna height and HR is the receiving antenna height. So look at this image. When start traveling from transmitter to the receiver, the energy of the signal will get decayed, will get normally reduced due to the various parameters because the wave is traveling in a free space, isn't it? So the electric field in the line of sight path is ELOH of d dash comma t which is equivalent to, we just rewrite the equation for a line of sight path where the distance in the line of sight path is calculated as the d dash. At the same time, we consider as t, and c is the speed of light. So in this equation, c is the speed of a light in a vacuum, where omega c is your carrier frequency. Okay. So look at this. This is the line of sight transmission source where there is a direct connectivity between your transmitter to the receiver. Both are in visible range. So we can rewrite the electric field equation for a line of sight path. The only difference is here we consider the distance to be d dash, which is nothing but a distance taken during the line of sight transmission. And whereas we consider the electric field in the reflected path. So the electric field in the reflected path is Ag. Here the distance is considered to be d double dash. Okay. And again the other parameters are similar. The only difference here we have shown is this reflection coefficient. Since here we consider the reflection phenomena, we are including this reflection coefficient. So the direct path which is included with this reflected path. So this is the equation for the reflected path, that is the ground reflected path. So this is the diagram which describes the above two equations. So look at here, this is a line of sight direction which is at a distance of d dash. That's what we included in the equation, whereas your reflected path take a distance of d double dash. So by considering these two parameters, we rewrite the equation for your electric field. And now we just look at the geometry. We extend the line from the receiver to the transmitter by means of this dashed line, isn't it? So this line touches your transmitter at this point. So look at here, from the ground plane up to the receiver, the distance is HR. That is, this distance is HR. Whereas the total distance from the ground plane to the transmitter is HT. So what about this point? So the total is HT, whereas this part is HR. So ultimately, the value is nothing but HT minus HR, isn't it? So using that, we are writing the electric field in total by considering the line of sight and as well as the reflected path. So the total energy is at a distance of d for the time small t is equivalent to, first we write the electric field energy due to the line of sight. So we write the equation and we add the effect of a reflected path with it. So here the reflection coefficient is perpendicular. So it is considered to be the -1, value of -1. So we are replacing the reflection coefficient to be -1. So we know all the parameters in this equation, isn't it? We already discussed. And we are applying the method of images. Okay. So already we have extended this dashed line, isn't it? And we calculated the distance as HT minus HR. So in the method of images, whatever we have at the ground plane will be reflected in the same way in the beneath of your ground plane, that is below the ground plane also. So we extend the transmitter which is at the height of HT from the ground plane to the bottom and the receiver in the same way. And again we connect them by means of a line of sight path, and now we extended the same line in the below path of a ground from the receiver to the transmitter line by means of the same dashed line. Okay, so now you look at the image. So from here to this point, the transmitter height is HT, whereas from this point up to this dashed line, the receiver height is HR, which is similar height, isn't it? So from this point to this data line, the total distance is HT plus HR, isn't it? So we are going to use this for calculating the values of D dash and D double dash. Okay. first we consider the triangle ABC. Okay. So consider this big triangle, okay, where we extend this D double dash to the bottom of your ground plane. So we just extend this line. We structured this towards in this direction. So we extend up to this point. So consider this triangle, okay, this big triangle where it is A, B and C, okay. So now this BC point is D double dash. That is the distance between your transmitter to the receiver. So using a Pythagorean theorem, we calculate the value for a D double dash. Okay, so this D double dash is nothing but the height is, total height from this point up to this transmitter is HT plus HR, and the distance between your transmitter to the receiver is D, isn't it? So this point is D double dash. So this D double dash is equivalent to square root of, here it is HT plus HR. So HT plus HR the whole squared plus the bottom value is D. So it's D squared. Now similarly we calculate D dash by using this small triangle. So in this triangle this D dash is equal to, we already calculated the value this to be HT minus HR, isn't it? So D dash equal to square root of HT minus HR the whole squared plus, so this distance is D, so plus D squared. Okay, so we are going to use this value for calculating the path difference. So path difference del is nothing but D double dash minus D dash. So we subtract these two values. And another consideration we are carried over here is when your transmission receiver separation is very large compared to the height of HT, that is your transmitter height plus your receiver height, the equation can be simplified by means of using a Taylor series. Okay, so we are approximating this equation to be 2HT HR by D, which is nothing but a path difference. Okay, so once the path difference is calculated, we can able to calculate the phase difference between the two electric field component and also the time delay. So the phase difference is theta del, which is calculated using the formula 2 pi by lambda into del. So we could rewrite this to be del omega c by c. Omega c is the angular frequency, and a time delay is calculated using del by c. Okay, so by substituting the value of this phase difference, we will get theta del by 2 pi fc. So these are the values of a phase difference and time delay. And when the distance between a transmitter to the receiver, that is D, becomes very large, larger the difference, and this D dash and D double dash becomes very small. That means all of them will be equivalent to each other. So in this case, the amplitude levels of both line of sight, reflected path are virtually identical. So we equate the magnitude part of all the three equations. So this is the basic equation, this is the equation for your line of sight, and this is the equation for your reflected path. So the magnitude will be almost equivalent, and by all these assumptions, finally we are writing the received power at a distance D from the transmitter will be PR, that is received power is PT, transmitter power, GT, your transmitter antenna gain, GR, receiving antenna gain, into HT squared into HR squared by D power 4, where HT, HR are the height of your transmitter and receiver from the ground plane, and D is the separation distance. And path loss is calculated using this formula. So with this, the ground reflection model is over. I think you will get a better idea about what is ground reflection and how the path loss and total power will be calculated at your receiving end, isn't it? So take up these questions for a better understanding of this class. Thank you, students.